All right, so we're back to regression. So just as a brief recap, and I like those recap sessions because it kind of keeps the momentum and kind of solidifies things in your memory. So we have regression. Regression basically builds on correlation. Remember that correlation basically is the sum of the products of the deviations divided by the square root of the product of the sum of squares. It has a built-in standardization procedure. So standardization in the same fashion as we did in chapter 6, when we standardized individual points according to the number of standard deviations, it was located away from the mean. The standardization procedure here is that you basically have those deviations and you have the product of the deviations summed up. So you have a marker of the difference from both sides, from both means, both dependent and independent variable. And you're dividing this by the square root of the product of the sum of squares. So you have an aggregated marker of that difference from the mean divided by a marker of variability. Thereby, you have a standardization procedure built in on which you're basically building on to carry correlation a little further and carrying it towards regression that basically allows you to predict a dependent variable. And the way you're doing that, you're utilizing the standardization by basically utilizing a standardized x, multiplying it by the regression or by the correlation coefficient to basically get to a standardized y hat, where the y hat is basically a predicted dependent variable. So whenever you see that hat, this is something that is being predicted. So please keep that in mind. Okay, so set y hat equals r multiplied by set x. And we have done this example. So you basically can predict each individual y hat by basically looking at a standardized x. And we have done this example, and this basically allows you then to quantify the regression equation, which is basically a simple line equation, which is a y hat, that's the individual dependent variable predicted, as a function of intercept, indicated as a plus b, which is the slope, multiplied by an x. So you have the intercept per definition is that y value, that dependent variable value, at the axis where x equals 0. So this is where the x-axis is being crossed by your line. Then you have the slope, and the slope per definition is the increase in the dependent variable or in the predicted independent dependent variable with an increase of 1x, an incremental increase. So basically what you need to do, if you have a line of best fit, all you need to be able to do is to remember the equation of set y hat equals r multiplied by set x, and you just need two x values. You need 0 and 1. You need to standardize a 0 and you standardize a 1. If you standardize the 0, you get your intercept. If you, in addition, know a standardized x of 1, you can predict your y hat for x equals 1. Then you can calculate your intercept that you have calculated here. And then you can calculate the slope by calculating the difference between that y hat at where x equals 1 minus this y. That is your slope. Alternatively, you can also use the fancier formula, which is y2 minus y1 divided by x2 minus x1, which basically is y2, that's the one with the higher corresponding x value, minus y1, which is the smaller one. That gives you that difference between here to here. And then all you need to do, you calculate the difference from here to here, and you divide that difference in y by the difference between the x values. By that, you automatically have a normalization, and you get that increase in the y value with an incremental increase of 1 on the x-axis. Is another way how to calculate it. So if you're being challenged at the exam with a question like that, you have 2 points, with the corresponding x values, you can calculate it as y2 minus y1 divided by x2 minus x1. Memorize this formula. You have it in the spreadsheets as well. So basically what we're doing in regression is, so we have data points. We try to make sense of these data points. You can predict all these data points hypothetically by just saying, okay, so they're all like the mean of y, the mean of the independent variable. So that would basically testing the variability of your points against the flat line of the mean of the dependent variable. And this is our total error. If we're taking the mean and we're subtracting each individual data point, and we're subtracting the mean from each individual data point, we're getting variability, which we know already from standard deviation, which is basically nothing else but our sum of squares. And that sum of squares in the context of regression, the sum of squares of the dependent variable is essentially that total error that we're quantifying later on. So now what you mean to do with regression, you're not satisfied now with the simple average of the dependent variable, you mean to improve it. And the way you're improving it, by basically you're tilting it and you're fitting it through your scatter, that basically goes through one particular point. And this is where the correlation coefficient comes in and the standardization procedure. Because the correlation coefficient gives you essentially a direction, but uses as the anchor point the mean of x and the mean of y. So this regression line will go through the mean of x and mean of y. And that's the reason for the regression to the mean. So now this being said, if you know now your slope and your intercept, you fit this line through your scatter, you quantify the distance of each individual point to that line of best fit, and that gives you basically a residual error. And these individual points, that distance from here to that line is called a residual. This is one residual, and the whole thing is residual error. And the residual error is naturally smaller than the total error because the mean as a prediction is just not a good prediction. If you tilt it and you kind of try to fit it through the means, you get a better prediction. And that's what you're utilizing for regression. In addition to that, what did I mean to say? Okay, so you're fitting that through, and you're doing that to minimize your squared deviation, your squared residual errors. Therefore, this method is called a least square estimation of that regression line. So this is the least square approach. There are other approaches, like a maximum likelihood approach, but this is the least square approach, which is common for ordinary regression analysis. So least square, with the idea that you keep that square as small as possible. So all predictions do have errors, and you basically you have to deal with that error, and you have to quantify it. So the way you're, bless you, the way you're quantifying it is by basically finding a standard error of the estimate. So the standard error of the estimate is basically nothing else but a t-distribution, as we have discussed already. We're quantifying the residuals. We have a certain distribution of these residuals around the mean. And this essentially will be distributing with a known standard deviation around the mean of 0. So the residuals, because it's being fit perfectly to minimize that squares, they're distributing around the mean of 0. So the standard error basically indicates then the typical distance between the regression line and actual data points. Will allow you then, utilizing the properties of a t-distribution, to do hypothesis testing and essentially determine a p-value for your standard error and your slope estimate, as we will see later. So when you're basically looking at these two predictions, you clearly see that both are somewhat different from each other. So they're not identical, right? So it's clear that the left one is a much more accurate prediction of the data, whereas the right one is less accurate. And this will reflect in what we're quantifying on the next slide, which is the proportional reduction of error. So now let's go back. So we have talked about the null hypothesis of a correlation coefficient. The null hypothesis is, and this is what we're testing with a correlation coefficient, and this is why we have an R table, which basically, with the standard error of the estimate, it's either a significant correlation coefficient or not. It basically tests against the null hypothesis of a flat line being accurate enough to predict all these points, which is the total error. Shifting it and using a slope to actually fit through this scatter will improve this prediction. And the quantification of that improvement is basically your proportional reduction error. So you get the residual error, and we will calculate this today, and we'll see what that means. And we have done it already last class. So you're calculating the distance of a predicted point from an actual data point. So this predicted point here minus that predicted point, this predicted point minus this actual data point. We're quantifying this residual error. We're getting this residual error. We're subtracting this residual error from the total error that we have in that scalar as a function of the subtraction from the mean. And we get, as the difference, we get that improvement. And that is actually the improvement conferred to by the regression equation. And this can be quantified as the proportional reduction error, or called the coefficient of determination, or simply R squared, which basically is the difference of the sum of square total minus the sum of squares of residual error divided by the sum of squares total, which essentially is a proportion, right? So we know we have a smaller fraction of something, which is the error that was explained away by your regression, divided by the total error. So this is a proportion of what was being explained by your regression function. So we have calculated this last time, and this is the visualization of what I talked about before. So we have here the flat line predicting all the points. So we see here quite a lot of residual error. That's the total error. If we're tilting this line, then we get a minimization of that error. Not tremendously, because it's only a univariate analysis, but it is still better. And just briefly, let's look at this calculation. So we have done this. So we have done this calculation, and remember this. So we have calculated here the sum of squares of the dependent variable. So that's basically the back depression inventory score. So remember, the example was back depression inventory score was predicted by the number of stressful life events. That's this graph here that we have just seen. So basically, the idea is the more stressful life events you have, the more likely you're depressed. We have a proportional reduction of error of 0.33. That means 33% of our error has been removed or reduced by fitting a regression equation through that. And this is what we quantified by quantifying our total error, assuming we're just predicting our individual points with one flat line, resulting in 788.1 score squared. Keep in mind that the sum of squares is the unit of this sum of square is whatever the unit of the dependent variable is squared. We talked about this briefly. I came across it at work in a different example with a lab value. So the value is always squared because it's a squared deviation, right? So the deviation is different. It's the difference between two values. So it's the same unit. But if you're quantifying it as a squared deviation, you're squaring it, and then the unit also is a squared unit. So it's this back depression inventory score squared. So this is our total variability, and then we quantified our predicted residual error. So for this, we first needed to determine our slope, our intercept, which we did here by calculating a y hat as correlation coefficient multiplied by a standardized set x. So we knew that where x was 0, our set x was minus 1.14. Excuse me. Thank you. And the corresponding y hat after multiplication with the correlation coefficient and basically unstandardizing it, we got to a y hat of 9.542, which is our intercept. Then we got at 1, we got 12.78. And the difference between 12.78 and 9.542 is 3.241. So that's our slope. Then we utilize these two variables to essentially calculate our y hat for each of our individuals. So for each individual, we calculate the y hat. Oops. We calculate the y hat by multiplying our stressful life events of each individual with the slope, and then add the intercept. Gets us the respective estimate y hat. The residual error is then simply calculated as the difference between our y hat minus our actual value. That gets us these residuals. So now the sum of these is 0, has to be. So is the mean. The residual error squared gets us to a sum of squares, a residual error of 526. The difference between 788 and 526 is 261. And the R squared is now 261 divided by 788. And that gets us this proportion that the regression function has now explained. So that's this proportion that we're quantifying. And today we're going to dig a little deeper into this. So this is the regression to the mean. Don't forget the regression to the mean, that this regression function always needs to go through the mean of x, mean of y. Therefore, all extreme values will basically, over time, in a time series, will always gravitate towards the mean for arithmetic reason. But what I want to get to is multiple regression. So we have now predicted the depression inventory score as a function of stressful life events, assuming that people will get more depressed with more stressful life events. So that may not be sufficient to actually have an accurate prediction, and that's quite logical, right? It's like stressful life events is not sufficient to predict if somebody gets depressed or not. Therefore, you may resort to multivariable regression. In multivariable regression, you include an additional variable into your prediction to improve your prediction accuracy. That is essentially allowing for you to be more accurate in your prediction and utilize it in a more accurate way. So for this reason, we have an additional data set, an additional data series. We have for these 10 individuals now also a sleep disturbance score. I guess everybody, well, you're now in college, so basically all of you have probably have had sleepless nights, and we know how debilitating this can be to not have a good night's sleep. So a sleep disturbance score is a potential contributor to depression. And that makes sense. It makes causally sense, and we will find out whether it also makes statistical sense. So the way you can look at this, so you can, obviously you can quantify the association between those two by basically just plotting them as a scatter plot and just see visually whether these two are actually associating with each other. So and you see already that there's quite a good correlation, except for that outlier down there that's kind of not too good. But basically, there is quite a good correlation with less variability than what we've seen of PDI as a function of the number of stressful life events. So thereby, it's gonna get interesting. So let's dig a little deep into this. And this is where Norton and Heinz are basically indicating that we should think of multiple regression. And we're gonna do this exercise next week on Wednesday when we have our lab day. We're gonna do this actually in R. And we will produce a software output like the one that you're seeing here in front of you. So this is an output from SPSS. So SPSS is just like R, Python, SAS, a statistical software that allows you to do statistical analysis. And it's quite common, particularly those of you that are inclined to go into psychology, you will likely have to work with SPSS. I'm not a big fan, but that's my personal preference. Good. So the way SPSS organizes that, so you see here the model outline. So the model outline contains here in a multivariable analysis with two variables. So multivariable is two or more variables included in the model. It basically contains the two variables, life events and sleep problems. It contains a constant. The constant in a regression equation is basically synonymously used with the intercept. It's nothing else but the intercept. You have your unstandardized coefficients, which essentially is nothing else but the slope. And this is how you also have to think of that, and that's how you have to include it then in your prediction. So you have here with the B, this unstandardized B, you have here that intercept. You have slope number 1 for life events, and you have slope number 2 for sleep problems. Around this estimate, you have a standard error that will allow you to see how accurate that estimate basically is. Then you have standardized coefficients that basically is here quantified as a beta, which is basically the which is a standardized but not de-standardized estimate. So standardized coefficients do, because they don't contain the actual intercept and they don't build an overall model, they give you kind of a weighting in the model. They're not really, at least in my world, they're not really used that frequent. You have, based on your standard error, you also get a T. You get an estimate of a T-score, which allows you then to basically do hypothesis testing, whether your slope estimate is indeed significantly better than the prediction of just simply the mean. So this significance, or this p-value, is then depicted on the very right. So I think it's quite central that you understand each of these components. Bless you. So what does this mean? So let's carry this over into our Excel spreadsheet. And let's utilize this equation to do some simple predictions. Okay. So we have now here our multivariable model. That's the multivariable model, and this is being used for the prediction. Then we have the model that we basically utilized by only quantifying it as a function of the stressful life events. So that's essentially our univariate model. Could you please change? Come on. So we have here a univariate model and we have a multivariate model. So this is univariate. And this is our multivariate model. Good. So the multivariate model, as I said before, we basically were treating these unstandardized coefficients like slopes. So it's y equals 1.194 multiplied by life events plus 2.089 multiplied by sleep score minus 4.117 for the intercept. So basically, this is the formula that we will be using for the prediction, and this is as per the computation in SPSS. So now we really want to see how it affects our prediction accuracy. For that, we first need to quantify our squared deviations, because that is our total variability, right? That's the total error. So squared deviations, step one. So squared deviations, as we know, is, oh, we first need the mean. So that's an average. Average, that's not average. This. And then we need the standard deviation. So now we have the means and the standard deviations. Now we need the squared deviations of our total error. That's basically equals our back depression inventory score. Oops, parentheses. Back depression inventory score minus our mean. That mean logged in. Parentheses closed, squared. We're calculating this for all our 10 subjects. We're calculating a sum. And we're basically done. So that's our total error. So the total error is 788.1. Simple, right? What do we need next? Next, we need our univariate model. So now we get an estimate. We get our y hat uni. So y hat uni basically is, as we've seen in last class, it's 3.24 multiplied by the number of stressful life events plus the 9.542. So this is 3.24 multiplied by the number of stressful life events plus 9.542. We calculate this all the way, we drag this all the way down. And now all we need to do, that's the next step, we calculate the difference now. So we have, so this is now residuals uni. That's basically our estimate minus the actual back depression inventory score squared. You can put this all the way down. We're calculating the sum. That basically gives us now the residual error of a univariate regression model predicting our back depression inventory score. So as we have determined last class already, if we want to now calculate, we can carry this formula. Let's bring this formula here. So the coefficient of determination is basically sum of square total minus sum of square error divided by the sum of square total. Is now r square equals sum of square total minus sum of squares residuals divided by sum of squares total. And that's the 0.33 that we also have quantified last time. So that's 33% of our total error is explained away by our regression model, the univariate regression model. If we're doing the same exercise now with our multivariable model, and we do y hat multi, we're basically calculating this as 1.194 multiplied by the number of stressful life events plus 2.089 multiplied by the sleep score minus 4.117. So that gets us an estimate that is purportedly more accurate. Let's see if that holds true. And we're doing that by basically calculating again the residuals. So we have residuals multi. So this is now the predicted multivariable value minus the actual back depression inventory score squared. Repeated for all individuals, and then the sum of all these residuals. So now we see this is substantially smaller. What is this? Why is it smaller? It's smaller because we have an additional variable in there predicting our back depression inventory score. That means that this leftover error that we quantified here as 526 is now, after inclusion of the sleep disturbance score, only 79. If we're calculating now the corresponding R squared, we will see that our model has explained now substantially more of that variability of that error than the previous attempt. So this is again, it's the total error minus the leftover error that gives us what was explained divided by the total error. So that's how it gives us a proportional reduction error. So now the R square multi is 0.899. So this is almost 90% of our error was explained now by fitting this model. In this context, I also want to remind you, basically I want to tell you that the inclusion of additional variables will always increase the R squared. It almost has to. It not just almost has to, it always has to. Because it's additional predictive power brought into the equation. So it will always increase the R squared. The problem that you have, and you kind of see it here with a negative estimate. So sometimes if you include too many variables, particularly if you include variables that don't have much predictive qualities and don't contribute much to your prediction, you're overfitting your model. If you don't have many data points and you include a lot of variables, you may be overfitting your model at some point. To avoid this to affect your estimates too strongly, there's an additional modification that you can do, which is the so-called adjusted R squared. So the adjusted R squared is basically an R squared that has been penalized for the number of individuals. So you see here, the calculation is 1 minus R squared. So that basically reverses it. That basically gets you again the residual error multiplied by the degrees of freedom divided by sample size. K stands for the number of variables minus 1. So if you want to calculate the R squared, so R squared adjusted, that's basically 1 minus R squared multiplied by n minus 1, which is basically 9, divided by n minus k minus 1. N is 10, minus k is 8, minus 1 is 7, divided by 7. Oops. Yeah. So your adjusted R squared is only 0.87. So you penalized it for the number of subjects and the number of variables. If you do the same exercise, okay, so this is R square multi adjusted. If you do R square uni adjusted, you do 1 1 minus 1 minus r squared, which is 0.33, multiplied by, now we have 9 divided by n, it's 10, minus k is only 1 for the uni, so that's 9 minus 1 is 8. And now you are again penalizing it, and you again get a smaller estimate. Most statistical software programs will give you quite automatically an adjusted R squared. With some, you do have a possibility to kind of choose whether you want adjusted or unadjusted R squared. Okay. Any questions? So again, keep in mind, we're quantifying first the total error. This is nothing else but the individual dependent variable value of each individual minus the mean, summing the squared deviations up to a total error. Then we're predicting using a univariate model, which is 3.24 multiplied by stress for life events plus 9.542. We're predicting the individual entry for each participant. We are essentially calculating then the residuals. We're squaring those. We're adding this up. That's the leftover residual error after use of the univariate model and using this for prediction. And then we do the same analysis for the multivariable model. We're using 1.94 multiplied by life events. That comes from here. We have 2.089 multiplied by the sleep score, comes from here, minus 4.117, which is the intercept or constant in the software output. Using this prediction, we're basically calculating the difference. We're squaring this, we're summing it up. We're getting a leftover residual error. This being said, the sum of squares total minus the respective leftover residual error gives you that explained error. And the proportion, the proportion that is representing that explained error in reference to the overall error is your R squared. That R squared can be calculated as either unadjusted or adjusted. If you have more variables, if you have a lot of variables, you want to focus on the adjusted R squared rather than the unadjusted R squared, because it penalizes it for the number of subjects or the number of the sample size and the number of variables included in your model, which is particularly if you have multidimensional data, a lot of variables, little sample size, then you really want to use the adjusted R squared. Good. So that was multivariable analyses, basically with the aim to quantify predicted outcomes or predicted values utilizing the variables at hand, the independent variables. Yeah, we will speak a little bit more on Wednesday next week. We're gonna do, we're gonna see what R can show. A lot of things that you actually want to pay attention to. With regression, you have the known assumptions, and we have discussed these assumptions, independent values. Independent values is particularly important in situations where you have repeated measures. You see often that mistake that people use repeated measures where each individual appears more than once in that data set, and then they're being used in a linear regression. You cannot do that. You should always only use independent entries. So each data point should be one individual. That's quite important. Also, what you always want to see is homoscedasticity. That means the data should not vary a lot at one end and then only have scarce data volume on the other hand. So that's important to keep in mind and quite central to conducting this properly. All right. The limitations are that correlation is very often used for retrospective data, and this is really the most often seen use case. So you have collected data for whatever reason or purpose. You have data from the electronic health records, or you have data from previous experiments or surveys or questionnaires. You're looking for signals in your data, and sometimes correlation is used in this context, sometimes even with the purpose of just exploration and kind of do only explorative analysis, kind of seeing where a signal could be. A scatter plot is a nice depiction of data because you see each individual data point, so you may see trends in there that are not visible for you with the naked eye when you just look at the data. So correlation is used quite ubiquitously, and particularly for retrospective analyses. This is the limitation that Norton and Heinzen state here. So you have mainly retrospective data as the use case, not so often for randomized data. It's partly, I disagree with that, because you can use regression in randomized trials, and it's actually an elegant way to use that. You can use it in various shapes and forms, so it's not strictly true the way they're presenting it here. But yeah, so most commonly it is found in retrospective analysis. That's true. Another downside is that the independent variable, particularly in univariate analysis, the independent variable is a scale variable. So it's the same concept as a correlation, where basically you have a scale dependent and a scale independent variable, and you're basically utilizing both for the prediction. If you have additional variables, it's also not true that that always has to be the case, because essentially, since it follows a t-distribution, you can actually use a regression with a dependent variable that is scale and an independent variable that is categorically. You can actually use this for hypothesis testing, like a t-test. That's actually, it's an interesting use case, and this is where regression overlaps with hypothesis testing using t-tests and also with ANOVA. So you will see in R, for example, when we're quantifying a multivariable regression, you will see that we're actually getting an F score and an R squared from an ANOVA. But that's beyond the scope of this class. So, yes.
Is there a limitation to regression? It's hard to extrapolation.
That's right.
It's hard to extrapolate because it's only causal.
Yeah, that's generally with all correlational analysis, you have that problem that just because you have an association, you do not have a causal relationship.
Regression, because it can't be used for extrapolation because it goes beyond the range of independent variables. That's the limitation. No?
It gives you a tool to predict something moving forward, right? It's the same conversation piece as you have, for example, you cannot predict something where you don't have any data. You can give an estimate. It's pretty much the same when you think of the stock market, right? It's like a lot of people from life sciences actually, they end up going to into finance analytics because they know the models and they know how to employ the models. Like the models that the stock market that is being used on Wall Street, these are autoregressive models that we use in some of our predictions. So it's not rocket technology, essentially, but they move on and they're very savvy in statistical analysis, and they make a fortune on Wall Street, right? That's one way to go. And so you basically you mean with regression to predict something that you don't really have at that point. And whether this is a time series prediction where you predict the future in a way, or you predict it within a population and you predict the risk profile of a diabetic patient compared to a non-diabetic patient, the concept remains the same. in some shape or form. But you're absolutely right. If you mean to predict something that you don't have data for, then you have a problem. Let's assume we have here a lot of data and you mean to predict here the back depression score for somebody who has like 12 stressful life events. Your model may be absolutely utterly useless. And you can't say.
I just account for outliers. It's sensitive to outliers. It doesn't account for them properly.
Because it has a regression to the mean problem. And that is a well understood problem. One way to go around this is to basically do subset analysis. You do subset analysis and you mean with a proper trend analysis in the subset of different chunks of data, you basically mean to see signals which are basically population based and strong, and you mean to use this to strengthen your extrapolation and your prediction in areas where you don't have a strong enough signal. But again,
how would you calculate causation?
You can't causation. Causation you can't establish with correlation. You can find. So there are the 11 criteria by Bradford Hill, which basically include replication, subset analysis, biological plausibility. So there are 11 criteria. There's no test for causation. It would be a randomized prospective experiment. Correlation and analysis per definition can only be in retrospective format, in a retrospective fashion, can only be hypothesis generating. Whole epidemiology is basically hypothesis generating.
Sorry to get you in a rabbit hole over here.
No. No, it's a great question. It's a great question. This is basically one of the main tasks of epidemiology, to generate hypotheses that you then essentially embrace and utilize for designing future studies. The problem with future studies is they cost a lot of money. So that research needs to be very solid, and everything you do to design that research and inform that research and the design of your future studies, that is task of epidemiology. And this is including how to deal with people with outlying independent variables. You define between exposure and outcome, and you mean to kind of find these associations and predict these associations with varying degrees of independent variables. But it is a very good question. Yeah. Yeah. Okay, coefficient of determination, unadjusted, adjusted. This visualization, so slide 21, 22, that illustrates quite nicely, again, the difference between total variability. So this is the flat line. Also keep in mind, the flat line is also the null hypothesis of a correlation coefficient. So you're testing that correlation coefficient and comparing it against the null hypothesis, that it's better that the correlation between two variables is better than just utilizing the mean of the dependent variable. So that's your total error. And you're comparing it against fitting a line of best fit through that, using a least square approach where you're minimizing your sum of squares. And then you calculate that minimization, to what extent you were able to minimize that R squared utilizing the R squared. All has to be kept in mind, and that goes hand in hand with Ruth's question, essentially, that there is a regression to the mean phenomenon. And the regression to the mean is problematic because you essentially build a regression model by utilizing the correlation coefficient and minimizing that least these squared deviations. But the correlation coefficient basically fits through the mean of X and mean of Y. And thereby, all outliers will always gravitate back to that mean. And when you use this to predict time series like Norton and Heinz mean to illustrate with the stock market example, all these extreme outliers will always gravitate back towards the mean over time. An additional aspect, if you look into multivariable regression, so we talked about regression being able to be used for the analysis of categorical variables as independent variables, where you basically can utilize regression to do hypothesis testing using, it's pretty much a t-test, gives you the same result, or as an ANOVA. The way you have to conceptually think about regression when you include in a bivariate model, so you have back depression inventory score as a function of stressful life events, and you include a second variable that is categorical. What it basically will do, it will split your population in two halves. So let's say people that are diabetic are more likely to be depressed as compared to people that are not diabetic. Let's assume this would be the case. You would, with a second categorical variable, it would mathematically basically separate these two groups from each other and would give you a slope estimate that is only applicable to that group where this actually applies to, that has a higher value. So it parallel shifts the regression line for the group where it applies, that has a higher or lower value, depending on which one you design to be the reference group. So that's the way how you have to think about the addition of additional variables. And yeah, what else? What else did I mention? Are we already ready to go to the last slide? So the last slide is actually, I really like this, that they're listing these things. So I think I mentioned it already once, but it's so mind-blowing. I don't know who of you has used, so nowadays everybody talks about ChatGPT. Did anybody try it? Who tried it? You tried it?
If you ask it, I don't cheat. If you ask it to explain things to you, it does. So for example, like I'm a nerd. I was reading, like I was brushing up on Kant or something for like a paper that I'm writing, and I didn't understand how like a German word fit into. He makes his own terms, like he takes it from the German language, but then also makes it with his own definition, because that's what all philosophers do. I didn't understand what the word meant in his context, and I needed to know what it meant. So I put it in ChatGPT and said, well, what does this mean according to Immanuel Kant only? And it gave me a nice big explanation of like how you define experience, but in like the classical German language, you would not see that. Like in everyday, I guess, speaking, you would know, in everyday like speaking German, you would not use that word. It is specific to like Kant, and like Martin Buber uses the same term, but they're philosophers. Right, but they explain it to you. It's very clever.
Yeah. The problem is just no, but that's good. Well, it's like so AI tools are here to stay, right? It's like they're not gonna go away anymore, and we got to deal with that. So whoever's gonna use ChatGPT is like, just make sure you cross-reference information, and you know that this can really be accurate. So don't embrace everything as the golden truth. So it's an ongoing conversation, as you can imagine, in the community, in the scientific community, right? Because it's you can literally ask ChatGPT any question that you want to ask, be it scientific, be it you can ask everything. It's literally it's built on text data of 45 terabytes. 45 terabyte, I think that's pretty much consistent with half of the books ever written in the history of Earth. So there's a lot of text, right? And it finds syntaxes in this. What's the plural of syntax? So it finds syntax algorithms in this 45 terabyte, and basically then uses either it doesn't use, or it kind of finds answers based on what you define as sources that you define to the question that you ask. So first, it's already super busy to understand your question. And once it understood your question, it basically interprets it in a way and then finds you an answer. So they are on several levels. There are a bunch of caveats. So it's like, it's not even clear it's going to understand your question. If it understands your question, does it have the means and does it have the resources to actually find the correct answer? If it finds the correct answer, is it able to basically employ that knowledge to your question? So it's kind of tricky. But why am I rambling on about this? So this is there to stay. It's not going to go away, and in some shape or form, it will find its way in our daily life. And this slide basically shows it has found its way in our daily life. So basically, whatever you are doing on your phones is triggering machine learning and artificial intelligence algorithms. It's around you. You being characterized as you speak in your phone, since Siri is nowadays listening on the iPhone without actually checking in with you, even while you're not using your phone, just while your phone is around. So it's basically used by apps and websites. It's used for the forecasting. It's in the simplest format, it's forecasting the weather. In the most sophisticated forecasting, it's basically knowing what you're going to do next. It's going to know where you're going to go next. It's going to know in which train you're going to go next because you had the same pattern over the last 5 days. Or it will anticipate what you're going to buy next. And that's where it's getting interesting. And there was the case that made the news because I don't know which retailer it was, but basically, so there was a daughter who ordered a pregnancy test, bought a pregnancy test in a shop using the quote unquote shopping number of her dad. And her dad only found out that the daughter was pregnant by basically getting a recommendation of prenatal vitamins in his inbox. So, and that made the news. It was a couple of years ago. So that's when there was more criticism about AI going on. So, but the story is here really that this is around you, your data is being collected and your data is being used. And it's quite obvious. And it will, not only will it know what you might be interested in based on your shopping behavior, it will measure the frequency with which you buy certain things, and it will recommend you within the time frame you usually would buy that item again, it will recommend you to buy it. In addition to that, and this is where it's getting quite useful for the actual retailers per se, they basically fill the warehouses, the local warehouses, with products that they know the population will purchase over a certain period of time at specific time points. In the simplest format, it's like it's being colder out there. People are more likely to get cold. We need more Sinex. We need more wicks. We need more tissues. So it's anticipatory shipping. And that's the only way how retailers can maintain the really short shipping timeframes and are actually able to keep the costs low, that this actually makes any sense. So it's fascinating. It's not per se the multiple regression that we have used now. It's a little bit more of a sophisticated model, but the basis is basically the same. All of this is basically either regression analysis or the more advanced logistic regression analysis. Yeah, let's not go too deep into anything beyond that, but little difference, those of you that are interested, regression analysis, you're predicting a dependent variable. With logistic regression, you're predicting probabilities of a binary event to occur or not. So you're basically utilizing the same principle of regression to predict the probability of something to happen or not. It's not the probability, it's actually the odds. And the difference between odds and probability is when I roll a die is 1/6 is the probability, right? The odds is 5/6. So it's 5 times, it's the probability of an event to occur, to not occur over the probability of the event to not. The probability of the event to occur over the probability of the event not to occur. That's the definition. So it's 1/5 for a die. So that's the odds. They're not the same. So it's P divided by 1 minus P. And you log transform that, and then you basically get the odds transformed in probabilities. A longer conversation. Okay, so that's all I had for today. It was a little bit of a recap of regression. We're going to see again on Monday. We're going to chat about chi-squared. Prepare for the quiz on Wednesday. And yeah, have a nice long weekend. Enjoy your holiday.
Randomness? You believe in randomness?
There's no randomness.
There's no randomness.
Why would there be randomness?
I don't think like randomness exists. Elon Musk.